today that earlier this week, Cold Quanta has announced the early access program for Albert, our quantum matter system on the cloud. So that's where I am today. I'm amidst the quantum core and our laser table for this specific system. So as a part of the program for early access, we'll be accepting up to 100 users from North America and Europe. And in a moment, I will be giving you a preview of just how Albert is going to work. And if you are interested in becoming a part of our early access program, you can request an account online, and I will put that link in the Zoom. Okay, I'll put it in at the end. Sorry about that. Okay, so today I'll quickly walk through the soon-to-be-released Albert interface, and you can see just how easy it's going to be to start pioneering with Albert. Before I start, the experts at Cold Quanta and some members of this webinar today have constructed an awesome library of learning resources that Ori mentioned at the beginning of the webinar. And they can get anyone up to speed on ultra-cold matter so that they can start to use our resources in their research, educational, or engineering projects. If you're new to cold atoms, or if we've piqued your interest today, our webinars are a great place to start with the basics. So regardless of your level of experience, you can really jump into experiential quantum learning using Albert coming soon. So the first step will be to create a free account on Albert. You can sign up to request the early access by the link that I'll provide at the end of this chat. And then as a free registered user, you will have access to all the tools that you need to create and explore with ultra-cold matter. All right, so let's jump in. So the Albert Cloud interface puts you in control of the generation, manipulation, and imaging of ultra-cold matter. Users may create and submit jobs from anywhere within our early access boundaries, and Albert will automatically execute them in our lab in Boulder, Colorado, and deliver you the results in a matter of seconds. So you can begin your journey by creating a cloud of ultra-cold matter and imaging it, and we call this sort of process the ultra-cold matter generator. We'll refer to all of these processes as jobs just because that's the way that they're delineated in our web application. So for each job, you'll start with a cloud of cold atoms inside the quantum core in Boulder, Colorado. This object that you're looking at right here. Underneath all of these cameras and optics is a Rebecca system like Ori demonstrated before. So the initial cooling steps are automated and are executed by Albert at the beginning of the job. Once your atoms have reached approximately 300 microkelvin, then they will be transferred to a magnetic trap where you, the user, will take over the control of the experiment. And that starts with a cooling process known as RF evaporation. The easy click and drag interface that you can see on the screen here will allow you to try out different cooling profiles to achieve a different state of ultra-cold matter. You can experiment with RF cooling to try and achieve a Bose-Einstein condensate and rubidium, or you can optimize a cloud of different properties for your specific application. So when your job is complete, you can check out your results in the Jobs tab of our web app. This database of jobs will include all the results that you've generated with Albert, and you can continue to build your knowledge base all in one convenient location. It also means that you can review and continue to work with the results of your jobs when the system in Boulder is offline. Okay, so the technique for imaging ultra-cold matter that we're employing here is called time-of-flight imaging. Time-of-flight imaging characterizes your atom cloud by taking an image of the atoms held in a magnetic trap, briefly releasing the atoms and allowing them to move freely, and then taking a second image of the atoms. In the few milliseconds after you have dropped the atoms before you track them again, they fly in random directions with a velocity that's dictated by their kinetic energy. And this is the phenomena that allows us to learn about the atoms just by taking pictures. So the pair of images that you've collected will contain characteristics of your cloud, the number of atoms, and their temperature distribution. This information is automatically calculated by Albert. To learn more about the system that you've designed, you can change how long you let the atoms fly around before collecting a second image and start to put together a good picture of what your cloud looks like as it expands. Albert automatically does all of the camera calibration and image processing and just provides you with the important information that you need to know about each job. So on the screen here, you'll see a job results page with the time of flight data from a previous run. The thermal or high energy atoms, which have not been condensed into a Bose-Einstein condensate, have flown much further from their original position, which would have been the trapped position, and that indicates that they had a higher kinetic energy. The condensed atoms have an extremely low kinetic energy, and that means that they've stayed very close to their original trapped position in the time of flight interval. So in this specific instance, Albert has calculated that we've got 42,000 thermal atoms and 5,200 condensed atoms. You can see also an image here of the MOT, or the magneto-optical trap. That's the intermediate cooling stage before you proceed with RF cooling. So in lots of our products, you are making something that looks just like this, MOT. So here's another run where you can see that we've created a totally different type of distribution. In this instance, we've got almost entirely thermal atoms. So they're still very cold, but almost none of them have condensed into that fifth state of matter, the Bose-Einstein condensate. So this was just achieved by altering the RF evaporation parameters. And those two totally different states of matter were generated maybe a minute away from each other. Okay, so now that you have supposedly generated some exciting new clouds of ultra-cold matter, you're ready to learn more. And you can do that with our barrier manipulator toolbox. This is your primary tool at the moment to interact with the quantum realm and conduct experiments using ultra-cold matter. Albert's barrier manipulator toolbox is a reconfigurable optical barrier capability, like Ori mentioned earlier. And you can use these optical barriers to poke, divide, and shuffle around ultra-cold atoms using light. This is achieved by shining a pattern of non-resonant light onto the trapped atoms through the atom chip, and this applies a tunable atom force to the cloud. This light pattern is generated using spatial light modulation techniques, so it's dynamically reconfigurable in time and frequency and intensity. So the barrier manipulator interface, like the ultra-cold matter generator interface, is super easy to use, and it's all just click and drag for now, at least. Quickly, you can reconfigure your potential in time, space, and intensity, and you can explore all sorts of exciting phenomena with unprecedented ease. So here we have some examples of ultra-cold matter phenomena that you might expect to observe in Albert using the barrier manipulation toolbox. On the left is an interference pattern of two overlapping condensates. Interference is a quantum behavior, and in this image, we are observing the wave-like nature of these ultra-cold clouds. On the right is a Bose-Einstein condensate that was actually split into two separate condensates using tightly focused beams of light. This is very similar to those that are used in Albert's barrier manipulation toolset, and these are good examples of the types of moves that you can hope to incorporate into the choreography of your experiments. So this last example is a more complex circuit of ultra-cold atoms arranged into an atom analog of a transistor in an experimental system which we fondly think of as Albert's sibling over at CU Boulder. This is really just the beginning of a brand new and super exciting field of research based on circuits of ultra-cold atoms called atomtronics. So I hope that you have enjoyed this preview of the upcoming release of Albert, Quantum Matter on the Cloud, and that you will join us as we can explore the myriad applications of ultra-cold matter from the comfort and safety of our own homes. Sign up today to become a part of the first user group through the early access program, or just to receive updates on the launch and the progress of Albert.